Hello everyone and welcome to this lecture. In this lecture, we're going to cover a very important concept that's called bias variance trade-off. All right, so let's take a look. So let's assume that we wanted to get a relationship between the employee's salary and the number of years of experience. So again, as a basic idea when it comes to developing a regression model, we have two variables, an independent variable x, which is we put it on the x-axis. We have the dependent variable y, which is salary in this case, and we put it on the y-axis. And what we do in general is that we go out there, we collect data. So we collected data for the first employee, and we said, okay, maybe when the employee had, let's say, fresh graduate, he has, let's say, 1 or 2 years of experience, we give them, for example, let's say $20,000 a year, for example, as a salary. But as this employee gets more and more years of experience, he becomes more valuable. So as you guys can see here, the salary tends to go up in this fashion, and then it tends to saturate. Okay, you're not going to give, like an engineer, for example, let's say like $2 million, that won't work. You're actually going to reach a certain state, certain level, where you pretty much stabilize at some point or saturate or plateau, as we call it. All right. So what we wanted to do here is that we wanted to build a regression model, which is simply can model the relationship between the number of years of experience and the salary. So in the future, we can use that model. Okay, so for example, HR professionals can go out there and say, you know what, now I have a new hire, okay, who has, let's say, these number of years of experience in this specific, let's say, department. And using that model, I can go and predict, okay, approximately how much salary I should give them, basically, okay? All right. So again, as I mentioned, fresh grads tend to have low salaries, as you guys can see here. As years of experience increases, actually this should, as years of experience increase, the salaries tend to increase as well. And as number of years go beyond a certain limit, salaries tend to plateau and they do not increase anymore, just reach certain kind of a flat level in here. All right. So what we could do, we can say, you know what, this is my perfect model. So the perfect model would look like this. Okay, so if I train a linear regression model, or let's say a polynomial regression model, or whatever model, and the model was able to give me the exact same, like this relationship, that would be perfect. That would be the true model. That would be the best model ever. Okay, all right. So we can use that model later on, again, as I mentioned, if we have another employee with, let's say 8 years of experience, I can go up, go to my model, and go here and say, you know what, this employee, we should give him this amount of salary, for example. All right, okay, looks great. So again, this is just a very basic idea. Okay, we didn't cover bias or variance yet, so let's get started. So as we mentioned before, we generally divide the data into two sets. We divide them into training data set and testing data set. And in general, what we do is that testing data set, it simply should not be or have never been seen by the model before. And this is very important. Again, there is a very important or common analogy that we make is that, if you have, for example, let's say a student and you are teaching that student, for example, you give them certain assignments. So they solve these assignments and they practice for the exam. In the exam, you don't give the student the exact same questions with the exact same numbers. That doesn't make sense. Then, then the process became just, like a memory dump, or just, you are retrieving information again, which doesn't make any sense. In general, you give students newer information. You give them newer examples or newer assignments in the actual exam, or newer questions, right? But the idea is the same, okay? So the features are the same, or the examples are generally the same. And the best student who will be able to generalize, who will be able to transfer the learning from the assignments to the exam, even though the questions on the exam have never been seen by the model before, or have never seen by the student before, okay? All right. So as you guys can see here I have the number of years of experience, here I have my salary, and here the green dots are the training data set, and the red dots are the testing data set. Okay, all right. So let's take a look at two models. Okay, So in order to explain the bias variance trade-off, what I'm going to do, I'm going to assume that I'm going to have a very simple model, and we call this model Model 1, and that would be a simple linear regression. Okay, so going to be just one straight line, and this straight line will be very rigid. Okay, which means I can't bend it. I can't increase the order of the polynomial. It's just going to be a simple linear regression model. And Model 2, which is coming up in the next slide, it will be a more complex model. It will be, let's say, 10th order polynomial. Okay, that I can bend it whatever I want. It has more flexibility built into it. So linear regression model uses a straight line to fit the training data set. So here, this is my training data, okay? And what I'm going to do, again, please recall, this is my perfect or true model. That's the best model ever. And again, as I mentioned, this is a training data set. So here we only, if you guys recall, here we have the training, the green, and the red was testing. What we're going to do here, we're only going to have the green data points. So we're going to only have the training data. And we have our perfect model. And here we have our training data set. Okay, looks great. And if we fit a straight line or a linear regression model here, as you guys can see here, okay, you guys can see that this line, okay, it's okay. Like it provides, you know, an okay accuracy or an okay fit. So linear regression model lacks flexibility, because we can't bend it, right? We can't bend it to have, for example, let's say the perfect or true model. So it cannot properly fit the data set, okay? So the linear model, we call it, has a large bias, okay? And this is a very important concept. So now this line has a large bias, which indicates that the model is unable to accurately capture the true relationship between the salary and the number of years of experience. So that's the first definition. When you have a model that doesn't capture the true values or the true fit within the training data, we call this line, or we call this fit, we call it has a large bias. Okay, all right. So in this case, the linear has a large bias. All right. So let's assume we have the exact same example. So here we have the exact same data points, and here we have our perfect true model. But in this time, I'm actually going to use Model 2. Okay, so we have Model 1 and Model 2. Model 2 has high order polynomial regression, which is more complex data. Okay, so let's take a look. So again, this is the training data, and here we go. That's my high order polynomial. Now I can be able to basically bend it whatever I want, you know, like as strong as I can. So high order polynomial model is able to have a very small bias and can perfectly fit the training data. As you guys can see, this is my new model, which is a polynomial model. And as you guys can see here, it has a very small bias, which means it's very flexible and was able to capture all the variations within the data, which is perfect. Okay, it actually looks perfect right now. I'm going to show you the limitations beforehand, afterwards. And high order polynomial model is very flexible, as I mentioned. So these are the two models that we have. We have Model 1, as you guys can see here. It's linear regression. It's very simple, and it has a very large bias. Okay, why? Because it doesn't perfectly fit the data points. And now I have, you know, like from the outside, a perfect model that can fit every single data point. It's what we call it overfitting the data. It's literally like understanding every single detail within the model. Okay, and we call this, it has a very small bias. All right. The problem is, this is not the whole story. Okay, let's take a look at the other aspect of the story. So as you guys can see here, I have the two models. Again, these two models are used during training. So first, I have my simple linear regression model, and here I have my number of years of experience. I have my salary. Here I have the first one, and here I have my higher order polynomial model with, again, perfect true model, as you guys can see, the blue line. Okay, and by comparing these two, you know, like obviously Model 2 looks great. Model 2, the sum of squares here is actually very small. If you guys recall, when we wanted to assess the performance of the model, what we do is that we calculate the residuals. We calculate the difference between each of the data points, okay, and the model that we have in here. So in here, we calculate the error signal between the actual 2 point and the model. we calculate the error signal here too. We'll calculate the error signal here as well. And then we sum up, if we wanted to calculate, let's say, the mean error, what we do, or mean square error, or mean absolute error, we calculate the error on each and every point, and then we obtain the absolute value, and then we sum all these points, and then we divide by the number of samples. Okay. Please, if you guys are a little bit confused, please go back to the lecture on regression metrics, just to give you an idea of how do we assess the performance of the model. So if you guys take a look at it here, you will find the sum of squares is large. Okay, as you guys can see, there's actual error that I can measure here. So this will be large. However, for the higher order polynomial, as you guys can see here, the sum of squares is very small. I actually later can even see the error because the line, the model, goes exactly through the points. Okay, all right. So the problem is, this is not the whole story. This is just, like part of the story. So if you guys take a look at the exact same models, but instead of relying on the training data, what we're going to do is that we're going to rely on the testing data. Okay, so now this data points, the model has never seen before in the past. Okay, and these are the red points. If you guys recall, I had green points, and then I had the red points, which is a testing data set. And you will find the actual, kind of the story changes completely, or changes dramatically. Now, for the linear regression model, there will be an error, obviously, which is again the difference between the true points and the model. Okay, so here we calculate the residual, and so on. And I will find that there will be an error. Okay, but again, this error is okay. It's very comparable to the error that we had here during training. However, for the polynomial model, the results will be horrible. Okay, the results will be like really bad. Why? Because this model, as you guys can see, was able to capture all the details, all the features of the training data set. However, when we change that to testing data set, as you guys can see here, the results are terrible. Why? Because this model, we call it an overfit model, which means the model just, works great. It's like, again, think of it as a student who was able to go there, learn all the examples within the assignments, and memorize all the examples with all the numbers, okay? But they actually don't understand the concept. They don't understand the generality of it. There's no generalization capability. They just memorized all the questions, and they went to the exam, and they just came up with new questions, and then they mess up. They literally went up, they got like a horrible GPA or horrible results, because again, it was working as kind of a memory dump. They learned all the details of the training data. However, they failed during testing. So as you guys can see here, based on this, during testing, you'll find that the linear regression model is better compared to the polynomial model. I don't need a model that works perfect during training. However, during testing, it fails miserably, as you guys can see here. Okay. So now, if we calculate the sum of squares, you will find the sum of squares here are small, and here for the complex, the sum of squares becomes large. And the polynomial model performs poorly on the testing data set, and therefore we call it has a large variance. And that's the next important concept or definition. So let's take a look here. So simply when we say variance, okay, when we say model has a large variance, that means it has a larger variability when it comes to results. So when it has a different performance on two different data sets. So during training, it performs something, and during testing, it performs something. As you guys can see here, the linear regression model has a very small variance. Why? Because the results are pretty much the same. During training, during testing, we change the data set. The results are not that great, but it's okay. However, for the higher order polynomial model, the results here were perfect during training, but during testing, the results are horrible. So that model has large variance in this case. And these are kind of the important definitions in the machine learning kind of lingo when we say a model has large bias or large variance. So let's take a look at a very important graph, which we'll call it model complexity versus error. So as you guys can see here, let's assume that I have on the x-axis the model complexity. So we're going to assume that we have a linear, very simple model. And as we move to the right, we're going to have more complex model. It might be polynomial, or it might be, here I just put linear and polynomial just for demonstration purposes. But let's assume here I have very complex, maybe artificial neural network, that can model like, very complex relationships. And here we have a very simple model, just two coefficients, simple linear regression model. And here we have our error signal, okay? As you guys can see, if we have a very simple linear model, okay, you will find that here the bias will gonna be very large, okay? Why? Because the model is rigid and it can't capture all the variations within the model or within the training data. But as we increase the complexity of the model, as you guys can see here, the bias will go down. The model becomes more flexible, it becomes more kind of smart. You can change, like the fit of the model to exactly fit our training data, okay? However, as I mentioned, if we have a linear model, we're gonna have an okay variance. We're gonna have a small variance, which means the performance of the model during training, we're gonna match the performance of the model during testing. So it's pretty much the same. However, as we increase the complexity of the model, here the model starts to overfit way more. And that's why you will find the variance goes up, okay? Which means the model loses generality. It loses its generalization capability. So the variance will go up. And that's a very important concept in machine learning, which we'll call it a bias variance trade-off, okay? So now I need to find the sweet spot. I need to find a point, okay, where there is some variance, there is some bias, but they are minimized. I don't need a model that does great during training and it performs poorly during testing. And vice versa, I don't need the other way around too. I need to find the sweet spot, a model that's a little bit was able to generalize on training and testing data. And that's why, if you guys can see here, the total error in green, it starts high, it goes down to a certain point, and then it goes up afterwards. And this is the point that I'm looking for. This is my optimum model or optimal model that I'm looking at, and that's what I wanted my training data to, or the training process to actually to stop at. Once I reach that state, then I'm gonna stop the training and I'm good to go. And what we're gonna cover, actually, like close to the end of the course, a very important concept, which we'll call it regularization. And regularization simply works by reducing the variance at the cost of adding some bias to the model. Don't worry about it so far, like right now. We're gonna cover what we call it ridge regression and lasso regression techniques to overcome this issue. But just for now, I want you guys to understand the difference between bias, variance, and bias variance trade-off. That's all what I want you guys to know up till this point. So if we take a look at kind of a comparison here, you will find that we have two models. The first model is a linear regression model, and it's simple. Model 2 is higher order polynomial, and it's complex. And model 1 has high bias because it's very rigid and not flexible and cannot fit the training data set well. Okay, as I mentioned, it has a very high bias. However, model 2, which is I can change, like it's way more flexible, so I can make it and bend it, like as I like to fit the training data. So model 2 has small bias because it is flexible and can fit the training data set well. However, model 1 has small variance or variability because it can fit the training data and the testing data with similar level of accuracy, which it's okay. It's not that great, but it's acceptable. The error is very comparable between the training data set and testing data set. And that's why we call the model was able to generalize better. Okay, and and that's what we call it. The model is able to avoid overfitting. So it's not overfitting to the training data. However, model 2 has large variance or large variability because the model overfitted the training data and it performs poorly on the testing data. Okay, so simply put, one model has high bias, small variance. The other one has small bias, large variance. And as I mentioned, performance here for model 1 is consistent between the training data set and the testing data set, and the model is able to perform or to provide good generalization capability. However, for model 2, the performance varies greatly between the training data and the testing data. And that's what we call it. The model has overfitted the training data. And we hate overfitting, okay? Even when we perform, let's say, image classification, in more advanced, let's say, deep network or deep learning, you will find that we need to assess the model based on generalization capability. We need to make sure that the model does not overfit the training data. And as I mentioned, variance measures the difference in fits between the training and testing. If the model generalizes better, the model has small variance, which means the model performance is consistent among training and testing. If the model overfits the training data, the model has large variance. And again, as I mentioned, our optimal scenario, when the perfect regression model that should have small bias and small variability or small variance. And the trade-off between the bias and variance shall be performed for ultimate results. All right, okay. And that's all what I have for this lecture. I hope you guys enjoyed it. Let's recap what we have done. So in this lecture, we covered a very important concept, which is called bias variance trade-off. And as I mentioned, in general, we have models that's maybe model 1 that's very simple, that can be very rigid, and it provides an okay results, okay? And that's why we call it has large bias. However, during testing, it's horrible. During testing, it actually provides good results as well. So it's an okay during training and during testing. However, for model 2, we have a much higher fit, okay, or a much better fit during training. However, during testing, it provides horrible results, okay, because this model has overfitted. And what we're looking for is that we're looking at a model that can reach kind of an okay bias variance and reach a point where we minimize the total error between the two. And this is kind of a quick table that look at the difference between model 1 and model 2. And that's all what I have for this lecture. I hope you guys enjoyed it, and please stay tuned. Best of luck, and see you guys in the next lecture.